Welcome back, students, on these online sessions on industrial metallurgy. So let us proceed with the next session. In this session, we'll discuss about an important rule that is used in physical metallurgy called the Gibbs phase rule. And these are the contents that we'll cover in this session number 6. You see, Gibbs phase rule is a mathematical expression as has been shown in equation 6.1. And this mathematical expression or equation shows a relationship between the number of phases that are present in a material system, the number of degrees of freedom that are available within it, the number of components which are comprising that material system, and importantly, the number of external variables which are affecting the phase relationships in that materials system. Now, one important thing, this rule can be used for any materials system. The condition is that the system must have been brought to the conditions in which it is lying under strict conditions of equilibrium. Means when a material system is at some given conditions of pressure, temperature, and composition, the Gibbs phase rule can be applied to that material system, but the condition is that the material system should have been treated under very, very slow conditions of heating, very, very slow conditions of cooling, that is strict equilibrium conditions. If a system has been brought to a particular temperature pressure condition with rapid cooling, rapid heating, then this rule is not applicable. So that's a very important thing. Okay, most generally what you'll see that for any metals or an alloy system, when it is being manufactured or when it is being treated to improve upon its properties, generally there would be only two external variables which are affecting the phase relationships of that materials system. One of the variables would be pressure and the other variable would be temperature. In some cases, we'll see that even pressure would be kept constant. But most generally, the two variables, the two external variables, which would be affecting the phase relationships in a material system are pressure and temperature. So this E that was shown in the last slide, this E most generally would be 2. So if somebody asks you what is the Gibbs phase rule and specifically the journal Gibbs phase rule, it would be P plus F is equal to C plus 2 as is being shown by equation 6.2. So P plus F is C plus 2. However, as the second bullet point shows over here, there are several other parameters, variables which can affect the phase relationship of a materials system. These may include electrostatic forces, magnetic forces, gravitational forces, surface tension forces. And if a material system has been kept under conditions where any of these variables is also significant, and if on changing such variables, the phase relationships are getting affected, then this too will get increased. If in addition to temperature and pressure, any of these variables is also significant, so the equation will get modified and we'll say, let's state the Gibbs phase rule under special equilibrium conditions. For example, let's take a case where 4 external variables have become significant, and on changing them the phase relationship can get affected. So in that case, for this type of a material system, the Gibbs phase rule would be P plus F is equal to C plus 4. Now students, let us come to the binary alloys with whom we deal most often. And in case of binary alloys, you'll see the processing generally takes place under atmospheric pressure conditions. The pressure is fixed at 1 atmosphere, and the only external variable that is affecting the phase relationships in the system, which is making a change in the phases present in the material system, the only variable is temperature. And so if temperature is the, see, composition is also a variable, but mind it, that's an internal variable of a material system. Here in the Gibbs phase rule, see, this Gibbs phase rule has come from the laws of thermodynamics, right? And we have only we have seen that it's only the external variables which affect the phase relationships of a material system if that equation has to hold good. So in such a case, when for a material system, and specifically this would be for binary alloys, when we process them, when we heat treat them, the only external variable that is affecting the phase relationships in a material system is the temperature. And if that's the case, we'll say the conditions are condensed, and we have condensed Gibbs phase rule. And condensed Gibbs phase rule is given by equation 6.4. It is P plus F is equal to C plus E. E is only 1, so this becomes 1. The question is, what is the significance of the Gibbs phase rule? A very obvious answer which would come from a large part from the audience is that, sir, out of 4 variables, if we know any 3 in that equation that you have been showing, as I showed here, if out of 4 things for a material system, 3 are known to you, we can find out the 4th one. Yes, that's true, but that's practically not a application of Gibbs phase rule, because if you know 3 of the things and you have found out 4th, suppose you knew F, P, F, and E value, and now you have found out C, or if you knew some other 3 values and you have found out F, that's true, but that generally does not give us great practical knowledge about a material system or any other practical advantage. The main advantage of Gibbs phase rule is that it helps us in finding out that whether an equilibrium diagram that was constructed with the help of some experimental methods, is that diagram correct or not. I repeat what I've said. See, whenever you prepare equilibrium diagrams, or what are also called phase diagrams or constitutional diagrams for any material system, these are generally constructed with the help of some experimental methods. And there is a great possibility that when the experiments were being conducted, or when the data was being collected, or even when the data was being interpreted, you might make some mistakes. And the final diagram that you construct with the help of these experimental methods might be containing an error or a number of errors. So Gibbs phase rule is a very simple and a very you can say indispensable tool which helps us in finding out whether the equilibrium diagram that has been constructed with the help of experimental methods, is that correct, or there is a flaw, or there is an error in it. And how do we go about it? See, take the constructed equilibrium diagram, go to every type of phase region, ask from the diagram that in a particular phase region, as I've done or discussed with you when we were discussing degrees of freedom, go to every region of the equilibrium diagram and ask the diagram how many degrees of freedom you have for the material system in this region. You will get an answer about the degrees of freedom. Now apply the Gibbs phase rule to all the regions. In every region, the answer to the degrees of freedom that you get, first from the diagram and then from the equation, there must be parity. The answers must be the same. If you even find a single region, a single phase region or a 2 phase region or a 3 phase region whatsoever, even if you find one region in your phase diagram where the answer to the number of degrees of freedom that is coming from the diagram and that is coming from the Gibbs phase rule is not matching, is different, that means there is something wrong with your diagram. The answer coming from the Gibbs phase rule can never be wrong. Gibbs phase rule has come from the first principles. The answer coming about degrees of freedom from the Gibbs phase rule can never be wrong. And if any diagram, when you ask the diagram in the way I explained to you in the degrees of freedom part in session 3 or 4, wherever we discussed it, or 5, if that answer is not matching, then you have to have a relook at the equilibrium diagram, because there is something wrong with the equilibrium diagram and you need to correct it. And we'll do it in one of the examples when we go to type 1 systems, Copernican system, and then type 2 systems, lead 10 systems. There I'll prove for you that, oh, the diagram that we have constructed with the help of experimental methods is wrong. And why it is wrong, again, we'll discuss over there. So This is one numerical that I've brought for you. You can go through this numerical. It says that find out the various degrees of freedom for a three component system with various number of possible phases. Now, in order to do this numerical, students, you must know that the minimum possible number of phases in a material system is zero. No, it's one. The minimum number of phases that can be observed in a material system has to be one. The minimum number of degrees of freedom present in a material system is zero. Degrees of freedom can never be negative. The minimum value is zero. Number of phases can never be zero. The minimum value is one. So keeping that thing, and if in a numerical nothing has been mentioned about the number of external variables affecting the system, you'll take the journal Gibbs phase rule, that is P plus F C equal to C plus 2. C already has been given as 3 over here. And now what we can do is we can start with the minimum number of phases that can be seen in the system. So when you take P equal to 1 and you apply in the Gibbs phase rule, you get 4. Then when the number of phases increases to 2, the degrees of freedom would be 3. Similarly, when you go to number of phases 5, the degrees of freedom would come out to be 0. Now you cannot further increase the number of phases, because then the degrees of freedom will come out to be negative, which is not possible. So these are the different number of degrees of freedom that can be observed in this material system, and these for these corresponding number of phases, and that's the answer to this question. I hope you enjoyed this discussion. Thank you so much for watching. Thank you so much.